Welcome to Pomodoro Joe for Sunday, February 5th, 2023. Today we're looking at LeetCode problem 438. Find all anagrams in a string. This is a medium problem, and the problem statement says, given two strings, S and P, return an array of all the start indices of P's anagrams in S. You may return the answer in any order. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So this is saying an anagram is just a rearrangement of the letters in string P. In computer science or as a software engineer, we typically call that a permutation. So this is saying look for all the permutations of P in S. All right, so with that, we will get started. 25 minutes on the Pomodoro timer, and here we go. So the first thing I will do is create my result. We need something to return. For now, we'll make it an empty list, and then we'll return that at the end. The next thing I'll do is look for any early outs. Now, if we're looking for permutations of P in S, if S is shorter than P, then we can't find any permutations, and we'll return an empty list. So, okay, now we get to the main part of the problem. It's very tempting to say, let's just go through all the permutations of P and then search for those in S. Now the problem with that approach is that finding permutations is actually a very intensive process. It's going to take a long time. Just finding the permutations alone will take a long time. That's not even counting the time it's going to take to search for those permutations in S. So there's got to be a better way to look for all these permutations. So when approaching this problem, I try to think about, well, what is the minimum set of information I need to identify a permutation? And in this case, since we're not looking for specific permutations or specific anagrams, we just need to identify the general set of information we need to find a permutation. So what defines P and all of its permutations? That will be the set of letters that are in P and the count of those letters. So for example, if P was cat, then the thing that defines cat and all of its permutations are 1A, 1C, and 1T. Okay, so I like to call this the fingerprint method because you're not looking for the whole thing. You're looking for just the thing that kind of identifies, the minimum piece that will identify this permutation. So I will call it FP for fingerprint. I don't know what the actual official name for this is. That's just what I call it. So fingerprint of P, and we're going to make this a default dictionary where the key is going to be the letter and the value will be the count of that letter. So we make it a default dict of int, so this way if we don't already have the key in our dictionary, it will default to 0 and we can add 1 to it. Now we will also need to have a fingerprint for our string S. But we don't need the entire string. We are looking for substrings within S that are a permutation of P. So for this problem, we'll actually be using a sliding window. So you can imagine this sliding window as defining a length of characters from 0 to the length of P. Then you'll slide that entire window along from left to right until you reach the end of string S. And looking for permutations of P within that window each step along the way. So we will need some fingerprint for our window. So I'll call it FP of W. So now we have the storage for our two fingerprints. We actually need to build up these fingerprints. So for a fingerprint of P, we just need to find the counts of all the letters in P. And that's it. For every character in P, we just increment the fingerprint for that character, and we're done. Now for the next part, we can build up the window first, or we can just go through S, building the window along the way, and then sliding the window. So I'm going to do that. Now to build our window, we'll need a start index and an end index. We'll start them both at 0. We'll move the end index at first by itself. Then when the end index reaches the length of P, we can start moving the entire window, which means both the start index and the end index. So because we're moving the window to the entire length of S, we just say, well, the end index is less than length of S. So the first thing we'll do is we'll just add the character at the end index to our fingerprint for the window. Now for this, I think I'll make it easier by actually creating a temporary variable c to hold that character. Now this isn't strictly necessary, and it might save us some time in memory later if we remove this and replace it with s at the end index. So now we've got our end character in our fingerprint, and at this point we need to check to see if we're sliding the window or still building up the original fingerprint. So if our end index is actually less than the length of p, and in fact it's going to be less than the length of p minus 1, because length of p will give us the length, length of p minus 1 gives us the last index in p. So while our end index is less than the length of p, we're still building up our first window. So we'll just add 1 to the end index and we'll continue. Now once we've reached p, or the last element in p, we can start checking to see if our Windows fingerprint matches our p's fingerprint. And if they do match, then we'll add the start index into our result array. All right, so now we've got our basic check. We need to start sliding the window. How do we slide the window? So we've already added the end element into our fingerprint, so we need to increment our end index. Now we need to increment our start index, but before we increment the start index, we need to remove the starts character because we're moving past this, the window is moving past the current start character. So we need to remove that start character from our fingerprint. So again, I'm going to make this easier on myself by just using a temporary variable for that character. So we remove the count from that start index, and now we can increment our start index. Okay, now one last thing, and this is where it gets a little bit tricky. We are comparing two dictionaries here, our fingerprint for P and our fingerprint for this window. Now at some point, our fingerprint for the window will go from having a character with a count of 1 to having a character with a count of 0, meaning that character does not exist in this window anymore. But that character will still exist in our fingerprint as a key value pair, with the key being the character and the value being 0. Now our fingerprint of P will not have any characters with a value of 0 because we built up P with just the characters that are in P. So we will have a mismatch. Even though the counts will be the same, our key value pairs will not be the same. Our key value pair for the window will have a key with a value of 0, whereas P just won't have that key at all. So if at any point we remove the last count of a character, we actually need to remove that entire key value pair from our fingerprint for the window. All right, so now we've removed our count of zeros key value pair. We should be okay to do our comparison. And I think that might be it. Let's give this a run and see if it works. All right, we pass. Let's go ahead and submit that and see if we pass. Excellent, we pass. Okay, it's not too bad. We beat 68% for runtime and 26% for memory. Let's go back and do a couple tweaks to see if we can improve upon this. I think we have a little bit of time. So one thing we can do is I have this temporary characters here. Let's just swap those out for the real character. So this will probably save us a little bit of memory and maybe even a little bit of time. Okay, just that minor change. Let's see if that buys us anything at all. Oh, I must have messed something up. Let's give it a shot. Hey, that does. That saved us quite a bit. We now beat 71% for runtime and we beat 97% for memory. That's really good. Okay, is there anything else we could do here? Well, there's one thought that comes to my mind. Well, there's a couple things actually. One, this length of p. We're calculating this over and over and over again. We could just calculate it once up here. So let's try that. Call it length of p, and then we can replace all the places that we actually call it. Okay, and we can do the same thing with the length of s. I don't think it saves us that much because we should only be calling it. Well, let's see. Let's try that. Not too bad, 78% and 99% for memory. That's pretty awesome. Let's try also replacing length of s, just to see. We might end up bumping our memory up a little bit, but that's okay. It doesn't really help us much. That actually drops us down for both runtime and memory. I think we did better with just having the 1. Okay, there are a few other things we could do. One is instead of deleting every time we reach 0, we could actually just pad our existing fingerprint for p with a bunch of zeroed elements. That way we don't have to do this check at all. It will take up more memory. It might take a little bit more time in the beginning, but it could be worth it. Anyway, I am out of time. I encourage you to try to improve upon this. There are things you can do. Clearly, we're only beating 97% of other algorithms. Sorry, not even 97. Yeah, our best was 78%. I encourage you to check this one out on your own. We're only beating 78% for runtime, which means there are clearly things that we could be doing better. Check this out, try it on your own, see what you can improve. All right. Thanks for watching. I hope you enjoyed this. Hope you had fun. Hope you learned something. And I hope you can go out and write better code.